so I've recently added a few new assignments on here. The 4.4 and 4.5 that you see, those have been there for a while. Let me zoom this in a little bit. Why it looks so small today. So 4.4 and 4.5 due tonight. That's related to n-unit growth factors and writing functions that match descriptions, whether it's given as a table of values or just a couple of points or sentences like we were working on in class on Tuesday. But those assignments are due tonight, so make sure you finish those up. Over the weekend, and actually in class today, you'll see there's a couple of lessons for 4.8. So there's 4.8 lesson 1 and lesson 2. It's just because there's a lot of different sorts of questions, and for it to not be an overwhelming lesson that just keeps going, it's split into 2 chunks. But we're going to do a lot of that actually together in class today. So if you have your laptop with you, or you can access this on your phone in here, you're welcome to just follow along. We're not going to all have exactly the same numbers, but we're going to talk about the ideas about what are logarithms, how we use them, how to understand what they mean, and then next week we'll be getting into how to solve equations that involve exponential and logarithmic expressions that are something beyond just figure it out in your head, kind of think your way into an answer, which we're going to talk a little bit about that today. So over the weekend though, or before our next class I suppose I should say, 4.8, there's 2 lessons in there. Like I said, we're going to be doing a lot of those in class today, but then there's also, you'll see Mod 4 Part 1 review. That's kind of a recap of everything we did with exponential stuff so far before today. Not so much on what your assignment is, the 4.5 assignment, the trickiest stuff, but just to make sure we've got those basics down. Because this is a rather long chapter with lots of different topics, so I kind of stuck in a little review in the middle here. But what we're going to talk about today about logarithms, the homework assignment for that isn't due until after we have another class. We can go over some more examples there maybe. We're going to finish up Module 4 on Tuesday next week and then move on. Now I know in your syllabus it says Gateway Exam 1 due next week something. The coordinator for the class doesn't have that organized yet, so I don't know if we're going to change the date on it. There's some kind of issue with converting it into a new format. I don't know. So I don't really know what's on it because I haven't seen it, and he says it's not ready yet. So I apologize. I can't tell you anything about it. It's like some basic skills of some sort that are things that you probably talked about in another class, but I honestly don't know what they are because I haven't seen it yet. So for today, what I'd like for you to do, if you can pull this up on your own device, you can, but I'm going to have this 4.8 lesson 1. I want to talk about exponential and logarithmic functions, how they're related to one another, what they are. But there's a lot of, this is the lesson part. There's a lot of reading in it. I'm going to skip to, because I'm sitting here, this first section. There's lots of videos built in that go over how all of this works. But what I want to do is just thinking about exponential functions. If you remember when we worked with exponential functions, something like f of x equals, and then we had to find a starting value and our growth factor, and then the exponent was our variable. Again, exponential functions are ones where the exponent is what varies and the base of the exponent remains constant. So something like 48 times 1.042 to the x. So like a 4.2% daily growth of something, whatever the story might be to go along with something like that. But in any case then, something like 3 to the x equals 81, that's not an exponential function, that's an exponential equation. But we could be looking at something like y equals 3 to the x and be wondering, well, when does y come out to equal 81? So, because 81, it's like, oh, well, that sounds like it's related to 3, because 3's make 9s and 9s make 81 when we multiply. So this should be something we could find an answer for. What value of x, what exponent on 3 is it that turns a 3 into an 81? 3 to the what power? Equals 81. Thoughts? 4, yeah. And if you want to break it down, it's like, oh, well, 81 is 9 times 9, and that's 3 times 3 times 3 times 3. Like a couple of pairs of 3 instead of thinking about them like 3 times 3 is 9, times 3 makes 27, times I don't know what that is. Oh, it's 81, because I could have split it up differently. But it's 3 to the x equals 81. We can solve this kind of mentally using mental math because it's a whole number answer. Because 3 to the 4th power would make 81. If it was 85 instead, I might look at that and say, well, I don't know what x is exactly, but it's a little bit more than 3, something like that. And a lot of exponential functions, or exponential equations rather, are not easy to solve. You can't just like come up with a number or write it simply using addition, subtraction, multiplication, division, because like, oh, so just subtract and divide and something, because you're trying to find the exponent. So if it was something like x squared equals 85, you're like, well, I can just write it as square root of 85 and I'm done. I know it's a little bit more than 9, and I can write it as square root of 85. But if I said, well, what if this is 3 to the x equals 85? It's like, well, x is like 4 point something, but how do we write what it is exactly? Not with a root, because I can't say an xth root of something, because that doesn't really help. I'm trying to figure out what x is. So it's a little bit messier. And so what we do to solve this issue of not necessarily being able to write precisely, but knowing kind of what the value is there's just another notation to use. So it's not an operation per se, but logarithms are a way to express a relationship between the base of an exponent and the result of having used some exponent. So the logarithm is a way to express what that exponent is in the instance of like per A, based on writing a 3 and an 81. Say, okay, to turn a 3 into an 81, we use 4. But in any case, just one more question in this section here. 2 to the x power equals 128. Any thoughts on that one? It's bigger than 4.
16?
I think it's less than that. That sounds that sounds right. I'm like 2 times 2 is 4, 8, 16, 32, 64, 128. Yeah, so just doubling repeatedly takes 7 factors of 2 to make 128. So I'm just gonna, let's see, let me pull up just a blank document. I don't even know what this is gonna, there we go. So if I say something like 3 to the 4th power equals 81, and let me zoom this in, oops. It doesn't want me to unexponent. All right, let's see, zoom to make this really big, and I'll make it bigger. So if I say 3 to the 4th power equals 81, that this was the expression that we were working on earlier. It said previously 3 to some power, and we were supposed to figure it out. Let me see if I can type properly this morning. Equals 81. So we figured out it was a 4 just by, thinking, right? So if we had something like, just to kind of repeat what I was saying, instead of having 3 to the x equals 81, if I had 3 to the x equals 85, well, I know that in this case, I would know that, well, x is kind of 4. It's close to 4. But that's not a really good way to write an answer. But we'd like to be able to express it. You shouldn't have to grab a calculator to write a decimal version of this. So what we use is logarithms. Logarithms, and I forget what the word origin of this is, like the meaning of it, but it has to do with rearranging. It comes from some Latin term for something or another, but in any case, we're going to talk about how 3 and 81 are related, or how 3 and 85 are related. And I'm going to do this in two parts. I'm going to have to go back in. But basically, in an exponential function, when we're dealing with a function, you plug in an exponent and you get the result. Like if I plug in 4 for x, I get 81 as an answer. And this might have been like, oh, find the value of some. This was just to figure out what x is to make this true. But again, in an exponential function, you pick a number for the exponent and you get out a result. But you're given the base to start with at 3. So like 3 to the some power, and you get to, pick various powers, and then the result obviously varies based on what you pick for the exponent. Logarithms also have a set base to them that doesn't change in the middle of a problem. The thing that varies is what you put into it. But if I want to relate 3 and 8, this base of 3, to an exponent and getting 81, exponential functions, I get to pick what I put in that spot where the 4 is, and then I end up getting an 81 in that case. So I'm going to type this first just because it's easier. Why did I do that? There we go. The logarithmic way to say the first expression, 3 to the 4th power equals 81, is to say log base 3 of 81 equals 4. This expression up here and the one that I just typed, those mean exactly the same thing. They're talking about the same relationship between all of those numbers. So this base is part of the problem. This 4 is the thing we were trying to figure out above. And this seems kind of more like a normal order to have things written out. What are you trying to find? Like if it's on the after the equal sign by itself, it's like, oh, we just figured out that this is 4. So in expressions like this, if you're given 3 to the 4th, that's just compute it, you get 81. But this one, I'm given the 81, and I do some computations, mental math, and figure out, it's 4. Now, what this means is this whole expression on the left-hand side here, log base 3 of 81, is how that's read. And let's see, let me type that. Log, or logarithm, base 3 of 81 equals 4, or is 4. Let's write equals. But the base of 3, just like in the exponential expression above, the base of 3 is something that's given in an exponential function. A base of 3 is something that's given in a logarithmic function. Logarithmic and exponential functions just relate the same pieces of information in a different order. So let me write out, we just were dealing with all numerical expressions, but if I had something like f of x equals 3 to the x, this is something that would have input-output pairs of like, I plug in a 4 and I get an 81. F of 4 equals 81. On the other hand, if I had a function g of x, which was log base 3 of x. Again, in both cases, the 3's are given. Function g, if I plug in 81, so that it looks like the left side of that expression, if I plug in 81, log base 3 of 81, the output is 4. So these two function structures, if you notice, plug in a 4, get an 81. Plug in an 81, get a 4. That they're just two ways of writing the same relationship. One in terms of, like, this is easy to use if you know what power you want. I can evaluate this mentally if I say, well, kind of at least. If it's whole numbers, I could find that. Like, 3 to the 2nd, 3 to the 3rd, 3 to the 4th. This looks really weird, but it's kind of thinking about this. It's like, well, what if I knew the outcome? What if I knew the result was some kind of 3 to a power? I had something like 85. I want to know, well, 3 to what power makes 85? I don't know, but I can write it like that. So this log base 3 of 81 equals 4. Let me just pop this in the middle here. If I want to solve this, I could have just answered this, 3 to the x power is 81. What is x? I could write this. X is log base 3 of 81. So I just happen to know that the value for that one's 4. If I wanted to solve this equation, 3 to the x equals 81, I could write x equals log base 3 of 81, because those two expressions are equivalent. I'm just going to copy this. Oops, not get rid of it. The wrong button. So 3 to the x power equals 81, x equals log base 3 of 81. Those are two different ways to say the same thing, and you can think of it as solving for x. That's how we solve for the exponent, is by not really doing something, but just rewriting it into a log form, rewriting it into a different format. So kind of like if I say, oh, x squared equals 17. What do you do to solve that? It's like, oh, well, you can say I take the square root of both sides, but what precisely does that mean? Well, you end up with, instead of having x squared, you have x, and the other side you have a symbol that wasn't there before, square root of 17. So it's just kind of rearranging or rewriting in a different form. In this case, the x kind of gets separated from stuff, where maybe you can think, oh, well, in the example you just said with x squared, it wasn't quite so mixed up into the middle, but it's just a matter of like what you're more used to. This is about the same amount of mixed in there. I'm just rewriting it, getting rid of the 3 that's under the x by saying, oh, well, I don't want to write this in terms of x as an exponent on 3. I want to rewrite it in terms of 3 as a base of a logarithm. And again, it's a weird word, but it's invented by people in the, 1600s? I think it was the 1600s. But 1600s in Europe, all scientific papers were in Latin and French for the most part. So it's a weird word, and we just deal with it. But it became common usage right away, and it stuck. Log base 3 of 81 equals x means the same as 3 to the x is 81. So this other example with the 85. Well, I could say that x is a bit bigger than 4, but if I wanted to say precisely what x is, I could say that x is log base 3 of 85. And that is a perfectly good answer. Just like saying square root of 17, it's like, what does that mean? It's like, well, the only way somebody knows what square root of 17 means is by understanding what's meant by the term square root, and by kind of knowing square roots of other things. Like square root of 16 is 4, so square root of 17 is a little bit more than 4. Kind of like this answer. This is something a little bit more than 4. I only know that because I know that, well, you can think of it in log term or exponential terms, but 3 to the 4th is 81, or log base 3 of 81 is 4. So log base 3 of something slightly bigger, 85, is slightly more than 4. Or in other words, 3 to the something slightly more than 4 power would make 85. Don't know what it is, but this expresses it. So it's not like something that you have to have a calculator and punch it in to have a real answer. This is a real answer to what's the solution, 3 to the x equals 85. That's a real solution to that. It's just rearranged in the same way that using a square root symbol is something you're probably more used to. Oh, you can just leave it in exact form, or leave it as a square root. Same thing here. You can leave it in exact form as a logarithm. And if you want to decimal for something, like maybe it's supposed to represent a number of days until something happens. Well, then, yeah, we're probably going to want to round it to a whole number and, something reasonable. But as an exact answer, this is a perfectly fine expression which represents a solution to 3 to the x is 85, although we know a little bit about its size. So there's a whole video about that idea. So this is question 2 in this lesson. Consider the statement 4 to the 6th power equals 4096. So that's exponential expressions. We're kind of used to those, seen them a lot. It's got all numbers, no x's or anything. But looking at this, there's 3 blanks to fill. It says blank is the exponent on a base of blank, needed to produce a result of blank. All right, so wordiness, but the first blank is an exponent on the base of something else. Oh, the base is 4, the base of the exponent. So this is the exponent. 6 is the exponent on a base of 4 that's needed to, or that does, produce a result of 4096. So just word-wise, these are the same words we use when we're describing logarithms, just in a different order. So this is kind of like our 81 and 85 question. Now we're just picking different exponents on purpose. So if I say mathematical statement, 4 to the 5.3 power is approximately 1552.09. Well, similarly, that means the fact that the exponent 5.3 on a base of 4 is needed to produce a result of approximately 1552.09. So in logarithmic form, just like with the 3s and the 81s and whatnot, if we're talking about an expression, if we wanted to represent the same relationship between, there's 3 numbers involved here. There's a base of an exponent, and a result. If I want to write this same relationship between those 3 numbers in logarithmic form, the 4 is still going to be the base. It's going to be the base of the logarithm, say log base 4. So log base 4 is a type of log. Log base 3 is a type of log. It's like the base doesn't change. Similar to what I was just saying with square roots. Square root is a type of root. There's a cube root, there's a 4th root, there's a 5th root. When you're taking a specific root, there's like a specific button on your calculator that you hit that goes with that one particular root. Log on its own is usually used to mean something particular, but just kind of like if I say, I'm going to take some sort of root, you're like, well, what kind of root? Square root, cube root, 4th root? Like you need to know what number root it is to evaluate it. Same with a logarithm. I need to know what the base of the logarithm is for it to mean something. So log on its own, like there's a base that goes with it, whether it's written or not. And unfortunately, for strange purposes, there's sometimes when they don't write logs, it can mean a few different things depending on the context, just because people are weird. But it's like abbreviating things and assuming things are understood. Log, LOG with no number written down below, in this textbook means 10. In computer programming books, often means base 2. It's just conventions of whatever, but log without a number written down below is used to represent, it's called a common log, and what's common depends on what industry you're in. And generally in mathematics, common log is used base 10. But base 2 is very useful for computer-y things. So lots of times they just don't want to have to write subscripts. It's very annoying, especially in the days of early typing, and even me typing on this. Writing subscripts is not the easiest thing, so just say, okay, when I write log, I'm going to mean log base 2, or I'm going to mean log base 10, because I'm using that all the time. It's common. So that's what's meant by common log in reality. But in this book, it's if you see something without a number down below and it says common log, those are indicating base 10. That's useful in general science and math a lot because of things like scientific notation, times 10 to a power of something or another, base 10. All right, so in any case, thinking about this first expression, not something that it asks in this lesson here, but it says 4 to the 6th power equals 4096. If I wanted to write that same relationship between 3 numbers using logarithmic notation, let's see, where's my cursor? It'd have to be with a logarithm. The base of this expression, of both of these, is base 4. So let me shrink that now. Where's my, come on. Log base 4. It's usually not capitalized, but if it comes out capitalized just because, not a big deal. But the base of the exponent is 4 in both of these. So if I wanted to write them in a logarithmic expression, they both involve log base 4. The other two parts of a log expression is what's the input to the log function, like what am I taking a log base 4 of? It's kind of like what am I taking a 4th root of? It has to be something underneath it. This on its own, like that doesn't have a meaning. That's like having a square root with nothing underneath of it. It's kind of like a thing to do or an operation almost. But log base 4 of something equals something else. So the input to a log function is equivalent to the output of an exponential function with the same base. So if I'm thinking about 4 to the 6th equals 4096, if I'm writing a logarithmic expression to write that, the 4096 is mixed into the middle, and the exponent, the 6, ends up by itself. Because the equivalent, like in terms of knowns and unknowns, the base is a constant, the base is 4. I can either plug in an exponent and get an answer, or have an answer and try to find the exponent. Those are kind of the two halves to things to do with exponential and logarithmic functions. Exponential functions are easiest to use if you know an exponent that you want to use and are just computing the result. Logarithmic functions are best to use if you have a result of having used some exponent and you'd like to know what exponent it was. So when you see a log expression like this, across an equal sign from a number, you can think, oh, that number is an exponent, 6. So in fact, this whole log expression is representative of an exponent. Specifically, it's the exponent that turns a 4 into a 4096, and in this case, we know its value, that exponent is 6. So we turn a 4 into a 4096 using the exponent 6. And similarly, the next line from this, I can turn a 4 into a 1552.09. Oops. Using the exponent 5.3. So you can see that just a very slightly smaller exponent gave us quite a bit smaller number. But then again, it seems to be like, oh, 1,000 versus 4,000. It's about 1/4 the size. Well, the exponent is almost 1 lower, and it was an exponent on 4, so that should make sense. I have almost 1 fewer multiple of 4, like it's almost divided by 4. So it should seem reasonable that it's nearly down to 5. No, it would be like, what is that, 1,000? No. 1056 or something? Whatever 4096 divided by 4 is. But in any case, these are the ways you could write those same two exponential expressions from the lesson in logarithmic form. The base of the exponent in an exponential expression, if you're converting it or rewriting it in a different way, becomes the base of the logarithm. And what's like mixed in the middle versus by itself gets reversed. The exponent versus the result of having used the exponent are in opposite places in exponential and log expressions. So I know I'm saying the same thing over and over, but from teaching math for quite a while, I know logarithms are confusing, and you have to once you get it in your brain, it'll stick there, but they're very easy to forget what they mean if you take a little bit away from it. So I just want to have you have some sort of ways to make sense of reading them, and not just try to remember I put this number there and that number there and then I switch something around. That's great if you can remember that way, but make sure you know what it means. So here's what I was just saying. In exponential notation, something like 2 to the 5th power equals 32 could be rewritten as log base 2 of 32 being equal to 5. So 2 is the base in both cases, the 5 as the exponent, in logarithmic form ends up being written by itself, or in other words, both halves of a logarithmic equation can be seen as being the value of some exponent. So video. There's some questions in here about converting back and forth, so we just did some of those. But just as a quick reminder, negative exponents, remember, mean reciprocals. So something like 4 to the negative third power being equal to 1 over 64, maybe not something that pops to mind right away, but 4 to the negative third power means 4 cubed and take the reciprocal, or the reciprocal of 4, 1/4, multiplied together 3 times. You can do those in either order. A negative 3 power is a reciprocal and a cubed in whatever order you like. So just that's what I wanted to point out about this. Remember what negative exponents mean. So negative exponent, if I were to write this in logarithmic form, that negative 3 would be by itself. The base of the logarithm would be a 4, right? And so the only other piece of this is this 1 over 64. So for this part B here, this isn't a pick all that are true. There's only one of these that's true. Which one has the pieces in the right order? The number 1, 2, 3, or 4 option? Yeah, looking at this, it should be this number 2 here. Log base 4 of 1/64 equals negative 3. So this negative 3 by itself means negative 3 was the exponent in exponential form. The base of 4 on the logarithm means we had a base 4 exponential expression. 4 was the base of the exponent. And then the 1/64 is the other part, the result of having used the exponent. Or, again, you could read this as to turn a 4 into a 1/64 using exponents, the exponent would have to be negative 3. All right, so there's a few questions here that are doing the reverse of that, starting with something in logarithmic form and rewriting it into exponential form. I want to give you a couple minutes to see if you can rewrite each of these 4 expressions, the first 2, from logarithmic form into exponential form, and then the second 2 the other way around. So the second 2 are more like what we were just doing. All right, anyone have a solution for A? Ideas? A? Yeah, what do you have?
3 to the power of 6 equals 729.
All right, 3 to the 6th power equals 729. Sounds good. What about the second one? Log base 4 of 1/64 equals negative 3. What would that be in exponential notation? That should seem familiar.
4 to the power of negative 3 is equal to 1/64.
Yeah, that's the question we just had in the last one. 4 to the negative 3rd power is 1 over 64. And that should seem true. These are things that you can kind of check if you want to pretty easily. Like, oh, 3 to the 6th power. It's a couple extra 3s multiplied onto the 81 that we had previously. Yep, that sounds right. Now, what about 6 to the 4th equals 1296 going back into logarithm form? Notice it says this is not an equation. I'm not done yet. But it says log. Log, what base am I going to have on my logarithm? For this one, it should be log base 6. Good. if you want to, you can use the little yellow arrow key to get the palette, but to do subscripts on here, if you just do the underscore, you'll see it turns it into a subscript. Log base 6 of what?
1,296.
To turn a 6 into a 1296, I need an exponent that is 4. So log base 6 of 1296 is a weird and unpleasant way to describe the number 4, but they're equivalent, so that means that's a way you could write 4. And the last one here should be log base 8 of 1/64th. To turn an 8 into a 1/64th using exponents, my exponent would have to be -2. Oop, I missed the equal sign. There we go. So you're okay with this convert back and forth? Converting back and forth between logarithmic and exponential function form or logarithmic and exponential expression structure can help you solve a lot of equations. And we're going to be focusing more on weird equations next week. But let's see, find the value. So there's a lot of expressions like this. There's nothing to do on a calculator really, I mean, other than if you just want to check your multiplication. But these questions here ask, then there's a couple questions in a row. Give the value of each of the following logarithmic expressions. So log base 3 of 81 is 4. And then it explained why, because 3 to the 4th is 81. So similarly with these questions, these aren't asking you to try to put something in a calculator. It's asking you, can you mentally come up with, or guess and check, how to turn a 5 into a 125 using exponents. 5 to what power makes 125? That's what it's asking you to do. And these are all whole number answers. Well, I will say integer answers because there's some reciprocals in some of the other questions. But so here we have like log base 4 of 1/16 is -2, because 4 to the -2 is 1/16, a reciprocal and squared in whatever order you like. So there's a few questions like that. So this is the more interesting ones, the estimating ones. So the expression log base 4 of 20. If I want to estimate this, I'm looking to find, in the case, and you can see in the description here, wants to know, let me expand this to get the rest of the words on there, because I blew it up so big so we could read it, and now it's, there we go. Value of log base 4 of 20 is an exponent on a base of 4, needed to produce a value of 20, right? The value of it, what we want to do is estimate it to be between two integers. Say, well, it's got to be bigger than something and smaller than something else. So if I'm thinking 4 to what power makes 20, what two whole numbers is that going to be between? Thoughts? 4 to, yeah, between 2 and 3. 4 squared is only 16. 4 cubed is definitely bigger than that, and 16 times 3, or 16 times 4 if you work it out, is 64. So it's definitely between 16 and 64. So the value of this log expression is between 2 and 3, greater than 2 and less than 3. Because 4 squared is 16 and 4 cubed is 64. And this one has the numbers at the end filled in there. And you can see that 4 squared is 16, 4 cubed is 64. Same thing with this log base 3 of 100. Like log base 3 of 81 is 4. There we go. So it's one of these two. Log base 3 of 81 is 4. That's not quite big enough. Log base 3 of 100 is looking for 3 to some power to turn it into 100. 4 is too small. I don't know if 5 is too small. Don't know if 6 is too small. Like, you check a few numbers and see what those results are if they're not, results powers of 3 that you know off the top of your head. But we're just looking for two consecutive integers. In this one you can see 3 to the 4th power is 81, to the 5th power is 243. So it's definitely, 100 is definitely in the gap between 81 and 243. So our value here is between 4 and 5. It's 4 point something, probably a lot closer to 4 than it is to 5, because 100 is a lot closer to 81 than it is to 243. But there's more questions like that. What I want to take a look at is, there's a lot of graphs in here. We're not going to focus on the graphs of logarithmic functions so much, but just, I'm not going to have you graph them, but just looking at these graphs. This is an exponential function, y equals 2 to the x. So it goes through, it doesn't only have integer values. When x is 1, can I click on it? Y is 2. When x is 2, y is 4, and so on. But the logarithmic function at the right has the reversed xy pairs. The input and the output are reversed. You'll see the function written at the top. It says x equals log base 2 of y, so that we can have these, y is down here and x is this way, which seems sort of strange, but it's the same input output, or the same combination of numbers as the input and output, but they're in reverse roles. So y equals 2 to the x and x equals log base 2 of y are exactly identical functions. If I flip-flop the axes, though, so that the input and the output are reversed, and, I can't move that one. I have to move it from here. I'll see it let's see, approximately. Let's see, 2 to the 2.01 power is 4.02. In the left graph, that's seen as y equals 2 to the x. 2.01 is the exponent, and 4.02 is the result of having used it. These are rounded off to 2 decimal places. In the right graph, it says x equals log base 2 of y. So when y is 4.02, log base 2 of 4.02 equals the x value, 2.01. But the x and y's are in reversed places here, just so that it's like the input and the output match what was in the function. The input is y and the output's x. But these are two different ways to express the exact same relationship between x and y. And so we have just what's easiest as the input and what works as the output is reversed between the two. So, like I said, we're not going to spend time on I'm not going to make you graph these, but just looking at the graph, you can see the reversed pairs, input output wise. And so, or if you're looking at these, we've worked on writing exponential functions for things like this. If this is an exponential pattern, which they do tend to do these sorts of things, we should be able to write a formula for that. And if I were able to write a formula, like a rule like this, for what goes through all those dots, I can give it a function name. I could write what does the opposite also, or that inverse function. What has the opposite input-output pairs, like the input and output have been flip-flopped. And we could write that function as well. And that's what this is asking about. So take a look at these. Let's see if we can write the exponential function. We have only 3 points here that are labeled, but this does go through 0, 1 also. But if you can find that initial value, which is 0, 1, and that fits the pattern here, and the growth factor or decay factor you can maybe see in this case, since the y values are shrinking. See if you can find that function for f of x, the thing that's pictured, and then we'll write the inverse. And then we're going to go on to the second half of this. I don't want to spend a lot of time on the graphs, but they're good ways to picture what's meant by this relationship. I'll put this up there. is it that our, I'll call it growth factor, the general term, what is it that we multiply by to get from 1 unit at a time, or a 1 unit growth factor, or 1 unit decay factor? What is it that we're multiplying by? To get from 8 to 4 to 1 to a half? Or is that, wait, 8, 4, yeah. We're multiplying by a half. I was just checking to make sure there weren't weird negative signs because I thought I saw one. We're multiplying by a half, yeah? So that's our growth factor, per se. And this is called, let's say, f of x. Initial value and growth factor, well, 1 and 1/2 or 0.5 to the x power. You don't have to write this 1 here if you don't want to, but I'm going to write it just because that way it looks like the same structure as we have before. You could also write it as 0.5 instead of 1/2. You know, says, okay, so that's a 50% decrease from unit to unit, a 1 unit decrease factor of 50%. But in any case, you could write it like this. There's lots of different forms. But if I want to write the thing that's the inverse of this, so this takes powers and turns them in, like, I put in an exponent and it gives me some power of 1/2 as an output. If I want to write the inverse to that, and it doesn't matter what letter I use, it says to use y. So I want to plug in some y value that should be some power of 1/2, and it gives me back out what the exponent was. Or in other words, it should give me 1/2 turns into the result, this power, some power of 1/2, by using what exponent? So this is all equal to the exponent. You can think of this as being the same as x equals log base 1/2 of y. The same as I could think of this as being y equals 1/2 to the x. So if you want to, bracket, sorry. So these two, two different ways to write the same thing. Notation-wise, we've been using function notation, f of x equals something. I could have easily, since I'm graphing this in xy axes and was using those letters anyway, I can say y equals 1/2 to the x. And the reverse relationship description, just solved for the opposite variable, x equals log base 1/2 of y. 1/2 was the base of the exponent. In the original expression, x was the exponent, gave me a result of y. In the inverse, y was the input to the log expression, giving me a result of x, the exponent. But just notation-wise, if I call the first one, instead of calling it y, if I call it f of x, the formula part is the 1/2 to the x. And this inverted expression, or the one that takes the result and gives us out as a value of that, the exponent, would be log base 1/2 of y. Since it says f inverse of y. If it said f inverse of q, I'd just put a q here. The letter isn't actually important. We were just using x's and y's because there was a graph. So you can see this table of values here for function g, -3, -1.2, 0, 1, 2. If you're trying to create a function out of this, that bottom half of that is probably a lot easier to use. Oh, 0, 1, and 2. What do those go with? You can maybe find the pattern from that. to write a function and then rewrite in logarithmic form by doing the same conversion. And again, if it's helpful to write out y equals instead of f of x equals or something like that, please do. It's not like one's right and the other's wrong. It's just there's two different notations, and this question happens to use function notation as to describe the pieces. But they're both relationships between two variables. It's just a matter of what we're focusing on in terms of why did they write g inverse of y instead of just writing x or something like that. Just preference. So in this table of values here, review from what we were doing again on Tuesday and last week, what's the 1 unit growth factor? And this one is growth. As x gets larger, y or g of x gets larger? Yeah, 6. All right, we're multiplying by 6 repeatedly. So whether I'm writing a logarithmic structured function or an exponential structured function, 6 is going to be the base of the logarithm, base of the exponent. So y equals g to the x. If I'm writing that original function, should just be something with 6 to the x involved. All right, and I can see it goes through 0, 1. There's my initial value. So 1 times 6 to the x. So written in the other form, it'd be a log base 6 of something. I just have to pick my something, right? Well, again, if I think of that first statement as saying y equals 6 to the x, I could rearrange that into logarithmic form as x equals log base 6 of y. And that's all we're doing with these. And there's some more examples. There's lots of videos in here to watch. So if there's specific parts of this that you're more interested in, like this is confusing, I want to see more examples, there's video examples built in. But yeah, I was going to say, I think that's the end. I want to take a look at lesson 2. The second part of this, just a little bit. This is about what I was mentioning before, 2 specific logarithms that are used frequently. One called common log, and as I said, it varies from like industry to industry, kind of like what is common. But math and general science, like math and chemistry and physics, common log is generally log base 10. So it will be in this class. Common log, easiest to type, just type log, don't type any other subscripts. But common log, log base 10, is useful because of scientific notation, times 10 to a power, and you're thinking about rewriting things and figuring out what powers, how much larger one thing is relatively speaking than another. There's some examples with pH, etc. There's the chemistry part. But powers of 10 are also useful because, well, it's really easy to see, like 10 to the first power, second power, third power, fourth power have 1, 2, 3, and 4 zeros respectively, and so on and so on. So thinking about writing things as powers of 10 or solving things that are base 10 equations, whether it's log base 10 or exponential 10 to some power, it's maybe easy to estimate what solutions, for what power it would be to be between two sizes based on how many digits are in the number that it's supposed to be equal to. Even if it's hard to estimate better than that, you can at least get it between 2 consecutive integers pretty easily. But base 10 logarithm is called common logarithm. You can write it with a base 10, but in math book, if you just see log and no number down below, it means log base 10. Now, there's 2 frequently used logarithms, and these are the 2 that get their own special buttons on calculators just because they're used the most. So on your calculator, you'll see a log button, and you'll see an LN button. This isn't I, that's a lowercase l. It's also a logarithm. natural log, and this is ln, and this is common log. And those are each specific bases of logarithms when they're built into calculators. So you don't get to pick the base on most calculators, depending on what version you have. If you have a fancy newfangled one, sometimes you can go back in and pick a logarithm with a specific base, but it doesn't matter because, as we'll talk about on Tuesday, there are a lot of properties of logarithms. They're all related to one another, so you can convert between them. Unlike with square roots and cube roots, you can convert something from base 2 logarithms to base 7 logarithms and anything else that you want. So there are two that are on a calculator that are the most frequently used, and anything else, if you happen to need a numerical decimal value, we can get it some other way by using those two buttons or something else entirely. But natural logarithm is base e. E is a bizarre number. You usually first encounter it in compound interest sorts of situations. Continuously compounded interest, if you're doing some story problems about finance, involves this number e that seems sort of mysterious. There's like 10 different ways to generate this number e, but like pi, it's irrational, and it doesn't come from any simple, it's not irrational in the way that square root of 2 does, where there's a quick operation that you can explain to say how you got it. It's a bit more complex, like with pi, it's like, well, it's the ratio between circumference and radius of a circle. Well, circumference and diameter, I suppose, twice the radius. With e, it's a little bit messier yet, but there's some things involving trigonometry that can be used to estimate e, just like there is for pi, strangely. But the most frequent one is something called a limit, which is something you won't learn about until calculus class, or the tail end of this one. We'll talk a little bit about what limits are. But the idea of a limit is really kind of something you've seen before, but just without those words. If the exponential graph that we said kind of flattens out in some cases, asymptotes, like if it gets closer and closer to something as you go on, if you graphed in a previous class like 1 over x, it's like, oh, well, it's got a horizontal asymptote of 0, because the bigger x gets or the smaller it gets far from 0, the closer 1 over x gets to be equaling to 0. But it can't be 0, it's just kind of approaches that. That's what limits are really about. And e is what happens if you take 1 plus 1 over x and raise it to the x power, and you make x larger and larger and larger and larger. I'll say as x gets closer and closer to infinity. What? So this part in here, if x is getting bigger and bigger, 1 plus 1 over x maybe goes from like 1 plus a half, 1 plus a third, 1 plus a tenth, 1 plus a millionth. So it's 1.0000 something when x is really big. But if you're raising it to bigger and bigger powers, it kind of balances out. So the inside's getting smaller, well, closer to 1, and the outside's saying, but multiply this together more and more and more times. Well, it does kind of level out to something, but it doesn't turn into 0, it doesn't turn into infinity. It turns into this number e, which is about 2.7. It's a little larger than that. And the value is listed probably here. Yeah, approximately 2.7183, which seems like, why on earth would I want to use that number? It's highly unpleasant. Well, compound interest formulas, we kind of used one a little bit last week, or was that Tuesday? I think it was last Thursday. But they have a piece of the function that's kind of like this. If you have like, oh, it's 3% interest compounded quarterly. And so we have like a growth factor of 1 plus a fourth of 0.03. And then we raise it to a power that's like, well, how many months do I do that for? Well, how many compoundings do I have? Well, for 4 times a year, for 10 years or something like that, that could be a big power. But if you're not compounding like 4 times a year or 10 times a year or 100 times a year, but all the time. That's like having this division by division by larger and larger numbers, making a smaller and smaller percentage, and raising it to higher and higher powers, more and more and more times that you get that interest. That's where this E sort of comes from. And that PERT formula, if you've ever seen that. In any case, E is a bizarre number. It's useful for calculating continuously compounded interest, or not just interest, but other things that are continuously growing at a relative rate to their current size, whether it's a population of bacteria grows relative to how much there is, assuming that there's enough like food or whatever you want to call it for it to live off of. It expands at a certain rate, like the mass of the population of bacteria grows at a certain rate relative to how much there is. Something like that isn't dependent on, well, let me wait till the end of the month and then we'll all have some more bacteria. This is kind of like always changing and growing. Or something could be shrinking similarly at a always kind of shrinking rate. Things like that always change. This E is involved in those formulas as well. The nice thing about it, it's not nice for doing by hand computations, but one nice thing about it that you'll find out in calculus is doing calculus-y things with E is very easy. Strangely enough, if I have a function, we talked about rate of change, and this is just kind of above and beyond what we're doing in this class, but I just need to mention it because this is why anybody uses E in the first place, because it's cool. But if I were to graph or look at a table of values for y equals e to the x, where this is approximately 2.718 to the x. If it were 2 to the x, it'd go through points like 1, 2, 2, 4, 3, 8, 4, 16. It's a little bit bigger than that because it's almost 3, right? But same sort of, it gets bigger and bigger. But for instance, let's say that there's a point here, 2, e squared, right? Right around this point, if I were to calculate the rate of change, average rate of change right around that point, as long as I'm not too far away on either side, if I were to calculate slope, the slope would also come out to be e squared. Now, you'd get a decimal form version of it if you're doing it by hand, but in calculus, it'll prove that at any point on a curve like this, the y value and the rate of change around that y value are the exact same number. And that's kind of cool. So a function, the values of a function and the values of how fast it's changing, even though it's changing all the time, the y values and that rate of change are always the same number. And that's the only function that happens with, other than the function y equals 0, which is always 0, and its rate of change is also always 0. But that's a very boring function. So, in any case, thought I'd mention that. So E is kind of cool. It's useful in calculus because of certain properties related to rate of change like that. It's otherwise not very easy to work with, but it's got its own button on a calculator, well, natural log, and E is also on there. But there we go. Just a cool factoid about the answer boxes on iMath. If you type in E, it assumes you're talking about the mathematical constant E, which is this 2.718-ish number. So you don't get to use E as a variable. As soon as you type in E, it thinks you mean a number, this one specific number. So we can approximate values of it. It's between 2 and 3, like I said, so something like e to the 4th, which is what this asks us to type in, is more than 2 to the 4th, 16, but less than 3 to the 4th, 81. So, okay, that makes sense. Like I said, it's unpleasant to work with by hand, whether you're trying to plot points or find values of something. It's not useful for those sorts of things. It's useful for other reasons, which we're not actually using those other reasons right now. But I did want to point out, every once in a while, you'll see a logarithm with a base of e written down below it, log with a subscript of e. But most of the time, you will not. You'll see this ln. And so you have to internally remember that this symbol means log base e. So if you see ln, or you think it's in, it's not in, it's ln, natural log, which, oh yeah, here it is. Latin phrase, Logarithms naturali. Okay, great. Although this obviously means natural. I don't know what the origin of the word logarithm is, like what that has to do with other things, like other words. But it is this relationship, we use it for this relationship between a number and powers of that number. So the rest of this lesson, we're going to talk about in class on Tuesday. So this lesson is due prior, but I want you to read about these logarithm properties. It's weird. It's better than me saying it. I'd like you, if you've seen them before, great, maybe you already know these. But I'd like you to try to read through this and make sense of what these logarithm properties are. They're related to exponent properties. It's just since logarithms are rewritten exponents, the properties seem different. But I'd like you to read through and see what you can get from this on your own rather than me talking about this. But we will, on Tuesday, we'll recap and talk about these sums of logarithms and differences of logarithms and multiples of logarithms and how to solve some equations using them. But just as I said earlier, and I'll just mention this one thing. So this equation here, log base 5 of 8x plus 45 equals 3. That's an expression that's written in logarithmic form. If you just rewrite it into exponential form, you have a perfectly normal looking equation that you could have seen like years ago without knowing anything about logarithms. Because in this expression, this means 5 can be turned into 8x plus 45 by using the power of 3. Oh, so 8x plus 45 must be 5 cubed, otherwise known as 125. So if this is really just 8x plus 45 equals 125, that's an easy enough equation to solve, right? Just subtract and divide from there. The trick to making it not look awful is rewrite it so that there's not a logarithm in the middle of it, so that you have this expressed in exponent form, where 5 cubed is something I don't have to write with an exponent, because I can just work out what that is as a regular integer number. So the remaining questions in here, however, use some of the log properties above to be able to do that. So I'd like you to try to read about these log properties and how to figure out how to what's called kind of condense multiple logarithms together. In most cases, that's what's going on. And that helps solve equations also, because then you can put them into a form like we just had here, have one log expression equal to a number that can be converted into exponential format instead, rewritten in a different way, at which point it looks like a regular algebra 1 equation. But some of these other equations down here, like log base 6 of 24x minus log base 6 of, like what? There's a log property above that shows you how to combine these together. They're both log base 6s. So just like if you have a couple of expressions with 6 to a power in them, depending on how they're connected, you can sometimes use exponent properties to combine or condense or rewrite. There's logarithm properties that are related to the exponent properties. But since logarithm expressions are exponents on their own, like log base 2 of 8 is an exponent of 3, the things that you're going to do with logarithms are the things that you would normally do with the exponents within an expression. So I'll let you read about that and work on the rest of this lesson. So again, the assignments, let me just get back to the beginning the fast way. The assignments over the weekend I'd like you to do. Module 4, that review from the first half of the chapter, and then finish up these 2 lessons, lesson 1 and lesson 2. The 4.8 homework, which covers both halves of that, won't be due until Tuesday night, but some of it's pretty easy. Some of it's very similar to what we just did in the lessons. But what we're going to do in class on Tuesday then is focus on some more of the log properties and solving logarithmic equations a little bit more with that. So we'll be good at that before we leave here on Tuesday. We'll get some practice. I'll have some like random questions for us to practice on, worksheet or something. But that's it for today. Study well. Make sure you keep track of these assignments that are due. You should be able to work on all of them. You don't have to finish up the 4.8 until after I see you again. But Tutoring Center is open much of the time. Atharva is going to have online office hours starting tomorrow, I think 10 to 11. I'll post a link in iMath and in Canvas to his office hours, which is really like, it's my office hours, but he's the host of them. So, all right. I will see you Tuesday, if not before.